Okay, so let's get started. The first thing I want to do is review Chapter 8, review the U.S. customary system, or they used to be called, I used to call them the English system versus the metric system. It's more properly called the U.S. customary system of measurements, and we'll start on the metric system as well. But today we're going to begin with a review of measurements. So the idea here would be, how are your measurement skills? Particularly, how are your metric measurement skills? But let's begin with a review of the U.S. customary units and so on. With the U.S. customary units, I want you to associate them with fraction math. Okay, fraction math. And the U.S. customary system, by the time you get into 6th grade, but especially 7th grade and 8th grade, they need to understand how to do what's called cancellation of units. So I want to review that. The Bob Jones 7th grade book refers to what I call cancellation of units. They refer to it as dimensional analysis. That sounds pretty high tech. I haven't quite figured out why they call it that. But when we are converting measurements that involve a particular conversion factor, we want to do them in fraction format. And we want to do, we're done with the elementary, larger to smaller, multiply, right? We're done with that, where we have to try to remember which one's larger, which one's smaller, and try to remember, do I multiply or divide? Which way do I divide? And all kinds of things. It seems to me that in elementary, many times students are programmed to always divide the smaller number, put the smaller number on the outside, the larger number on the inside. That doesn't work beyond 3rd and 4th grade, does it? Okay, they're programmed to do like subtraction. The minuend always has to be the bigger number, the subtrahend the smaller number. That's not true with subtraction when she gets to algebra, but it's true, of course, in arithmetic. It's certainly not true with division. You don't automatically put the smaller number on the outside and the bigger number on the inside, or the bigger number is the dividend, the smaller is the divisor. That's not the case. So division order is important, and that's why we're going to use fraction math, and the so-called dimensional analysis is using multiplication. We're going to always multiply by the conversion factor, and we're going to set this up so that the units cancel. This allows you to be able to do any conversion, whether you know the relationship between the units or not. And even when we start getting the messy decimals, when we do English to metric conversions, we're still going to want to use this technique. This technique is a critical conversion technique for chemistry when you have to change units. It's also a critical technique for physics when you have to change units from, let's say, miles per hour to feet per second. Or if you have to change feet per second to meters per second. Different conversion facts that are necessary, especially in science class. So when we are doing U.S. customary units, learn how to set them up by cancellation of units. And the 7th graders have to do it this way, and it really throws them for a loop. They want to just do the math real quick on the side, especially the easy ones. But then we're not learning the technique properly. So U.S. customary units, fraction math. So what do we do with remainders if we're doing U.S. customary units? What are they? Fractions. No decimals allowed. Students in junior high, and some of you probably have the same ailment, it's called fraction phobia. And actually fraction math is more accurate and fraction math is easier. Okay, so what we want to do is not avoid fractions, but use them, embrace them, make them a part of your math skills, okay? So when we are doing our U.S. customary units, we have to know the measurement conversion facts, and we need to set them up using the cancellation of units. So as a review, the problem with the U.S. customary units is you do have to memorize. And most of the time for our students in Fairhaven Baptist Academy, it doesn't matter because they've been drilled, starting with Mrs. Brader all the way through Mrs. Haiti, all the way through 5th and 6th grade. They've been drilled the measurement conversion facts. So let's make sure that you know your basic measurement conversion facts. In section 8.1, we have the length measurements. All of those are pretty familiar. Make sure you remember mile, 5,280 feet. So if we look at our U.S. customary units, we know that 12 inches equals 1 mile. We know that 1 mile. 12 inches equals 1 foot. I'm already down to the bottom of the list. 3 feet equals 1 yard. And then we know also that 36 inches also would be the same as 1 yard. And then 5,280 feet is 1 mile. I wanted to be done. Skip to the mile first. You'll notice that it used to be in the U.S. customary system, inches were abbreviated with a period and so forth. More and more that period is no longer written. It's no longer used in our textbook. If you look on section 8.1, you'll see every time they're dealing with it, they just put IN, no period, FT, no period. So I guess that's English. So it's no longer necessary, even in the U.S. customary system, to use a period on the abbreviations. It's just been dropped off. You'll notice in our textbook they were a little bit inconsistent. A few times they have a period, other times they don't. I do know that more and more, no one is using a period on the abbreviations for units, whether they're U.S. customary and certainly not metric. Metric has never had them. So that is something that you're going to notice more and more. There will not be periods behind math abbreviations. And more, there will not be commas until you get to the 10,000ths place. You will not see this. We'll start using the commas once we get to 10,000. Okay? And that's kind of gone the way of the dinosaur using commas here. And that's because we tend to read that as 5,200, don't we, instead of 5,280. So make sure you know your basic units of length. Those are so familiar to us. Also the basic units of weight, ounces, 16 ounces in a pound, and 2,000 pounds is a ton. That one's obvious from just being in the United States. But then the capacity ones, there are 8 fluid ounces in a cup. 2 cups in a pint, you know that. Also there are 16 ounces in a pint. Often you might see that one. 2 pints in a quart, 4 quarts in a gallon. Less common would be the dry measures used for produce and agriculture. We do have pints as a dry measure, all right? And we have quarts, and we have pecks and bushels. So even though we don't use them so much, you might see that there are 8 quarts in a peck, 4 pecks in a bushel. But those are dry measurements, pretty much reserved for agriculture and farming, not commonly used in math or science. So your U.S. customary units you've had memorized your entire life. So what we need to review and what we need to get down is the cancellation of units technique, and it really needs to be taught to junior high students, maybe even a little bit in 6th grade. And so when we do our cancellation of units, we're not worried about memorizing larger to smaller multiply or larger to smaller divide. I can't even say it right. So What we do is we always set these up so that they cross cancel. So if we want to do some simple measurement conversions, we have to start dealing with, in 7th grade, rational numbers. All right, so let's say we are going to convert 12 ounces into a pound. Don't need the period. Is 12 ounces an entire pound? No. So our answer needs to be in a fraction. The cancellation of units technique, in the first fraction, we put our given over 1. In the second fraction, we take our conversion fact. 16 ounces equals 1 pound. And we set this up so that the unit we are converting out of cancels. And notice it's always a good idea to use cursive when you're writing letters in math class, because otherwise you cannot tell the L from the 1. So always write lowercase letters in cursive, and that's also a problem in algebra. We want to use cursive on our letters so that we don't have trouble distinguishing the two. This will be correctly set up when we can cross cancel out of ounces and be left with pounds, and you can see that fraction math gives us the correct answer. 12 ounces is 3/4 of a pound, not 0.75 pounds. It's 3/4 of a pound. And here, when we are doing measurements, what becomes critical are the units. The units. You need to be picky as a teacher on units. Units put the answer in context. And so we don't want to be teaching our students and propagating the bad habit of calling this a label. That's not a label. That is part of the computation. We are doing ounces to pounds. And in here, the units are going to guide us through the problem. If we let the units help us set it up, we don't have to spend any time deciding, are we going to multiply or are we going to divide? We're always going to do fraction multiplication, and we're always going to cross-cancel the unit we want to eliminate so that the unit we're supposed to convert into remains. So cancellation of units has two advantages. First advantage is we no longer decide, are we going to multiply or are we going to divide? The second advantage is that it employs the units, and it shows the students that units are so much more important than just a label on the end. We're not doing a little story problem here in 2nd or 3rd grade where we label 7 pencils left, and they have to put the keyword and you label it and so forth. Units are not labels, units are part of the answer. This number 12 has no context without ounces. So it's 12 ounces, it's not 12. So when we read the answer, when I say the answer, when students say the answer, when students set up the problem, they never say 12 by itself, it's 12 ounces. 16 ounces, 1 pound. The answer is not 3/4, the answer is what? 3/4 of a pound. So units are not labels, units are part of the problem, especially when we have standard units in measurement problems. Don't allow them to give the answer without the unit. That's not just a label that I slap on the end. It's part of setting up the problem, and it's part of solving the problem. So as we are doing our review of U.S. customary units, we are going to stress the units. We're going to use the units to set up our problem, and we're going to follow fraction math, both in how we set up the problem and how we express any remainders. No decimals allowed, okay? On any assignments that you do for me in the U.S. customary system, whether it's on a quiz or on chapter, you have to do the chapter 8 review and test at the back of chapter 8. All remainders are expressed as fractions. Our answers are mixed numbers, whole numbers, fractions, no decimals, no mixed decimals. Okay, so when we are setting this up, the other advantage is we can do a multi-step conversion. Let's say I have, 540 ounces. How many gallons is that? Multi-step. I don't have to try to decide, okay, am I going to divide by, what am I going to divide by? How many ounces? I don't have to remember how many ounces in a gallon. I have my given measurement, and I know that there are, I can go straight to pounds. I know that there are 16 ounces in, not pounds, pints in a pint. I know that there are 2 pints in a quart, and I know that there are 4 quarts in a gallon. So I don't have to try to figure out, am I going to divide by 32? Am I going to divide by 64? No, I'm going to divide by 128. And I'm going to express my remainder as a mixed number, as a fraction to get my mixed number. And of course, I'm going to, you can see, there's 128 ounces in a gallon, because 16 times 2 is 32, 4 times 32 is 128. But then I'm just going to start doing the easy part here. 2 goes into 540, 200, 1470, and 270. And then 4 is going to go into 270 6 times, and that leaves 30. Oh, 4 does not go into 270. 16. So what I'm going to end up doing is 270 ounces. All this stuff is gone. I'm going to, oops, not the gallon. So 270 divided by 64. So how many gallons is that? They're both even. I can go by 2 again. Let's go by 2 again. 2 goes into 64 32 times. 2 goes into 270. 135 gallons. 32 into 135 is going to be 3. That's 696. Wait a second, I'm having math skills problems today. What's the answer? Maggie, you got it?
I got 4 and 7/30 seconds.
4 and what?
7/30 seconds.
That sound 7/37.
Seconds.
30 seconds. So how'd you get a 7? 30 seconds. All right. So that's about 4 gallons. So cancellation of units. Yeah, 3 goes into 13 4 times. Where I was getting 3. I was thinking, I don't know what I was thinking. So, all right, cancellation of units. But with the U.S. customary system, you do have to know your conversion facts. There's no way around that. So can you do U.S. customary conversions, whether we're going down to a smaller unit and we're going to multiply, or we can go to a larger unit like we just did the gallons and express your remainder as a fraction. So we need to be able to do that. Another thing that causes a problem in U.S. customary units is this. Let's say I have 1.5 pounds. How many ounces is that? Fraction math. Fraction multiplication. So what do I do when I do fraction multiplication? What do I do with a mixed number? Improper fraction. I put it in rational form. So this becomes 3 pounds over 2. And then I go to my 1 pound equals 16 ounces. So I'm going to do everything in fraction form. If I have a mixed number involved in my given, it goes to improper fraction form. We are just doing fraction multiplication. And your students are going to want to do 1.5. You probably want to do 1.5. 1.5, let's not mix and match our decimals and fractions. So what we're going to do is mixed number. Goes down to improper fraction, just like always. And then it becomes a very easy problem. 24. Okay, so everything cancels. Cross cancel the units. We're getting rid of our pounds. We want our ounces to remain. And so 24 ounces. Okay, my 7th graders still have the bad habit of saving the units for the end. They'll do a problem on the board and they'll not even write the ounces. Okay, put the units. The units put the answer in context. The units are part of the computation. We let the units guide us through the problem. So this is actually a multiplication by 16. So everything about our U.S. customary units deals with fraction math. No decimals allowed, and it's done in fraction format. That brings us to what we call compounds. And this is another disadvantage of the U.S. customary system, is we cannot reconcile our units. So what we do is we have to do compounds. Okay, and for example, the easiest compound maybe to start with, and the easiest compound for your students will be height. Okay, Morgan, how tall are you?
6 foot.
6 foot even. Anna, how tall are you? 5'2". Good. Because what are we going to do? What are we going to do? We're going to have to borrow. And do we borrow like decimal and whole number math? Our borrowing is much more analogous to fraction math, right? If I have 6 minus 5 and let's just say 5 and a fifth. Actually, 2 over 12 is a sixth, so we'll do that. What do? I borrow from the 6 in terms of the common denominator, don't I? And the answer here is 5/6. Well, the subtraction borrowing is the same with this, with measurements. I have to borrow an entire foot. So I borrow in terms of the conversion fact. It's very parallel. It is fraction math because the second unit is a different term, a different denomination, just like this is in different denomination, has a denominator. So my answer is 8 inches, very parallel in procedure to fraction subtraction, has to be borrowed in terms of the denominator. Compound measurement in the U.S. customary system has to be borrowed in terms of the conversion fact. You know that, right? And that's the parallel. We have to borrow in terms of the unit, not tens. Can we bring it down over here? Can we bring this down? No, we can't. Can we bring this down? 1 foot, 2 inches. There's not that much difference in your height, is there? Okay, so compounds are another area that must be addressed in the U.S. customary units. When we are doing our measurements, we have to deal with compounds. And it is very much parallel to fraction math. What do we have to learn in fraction math? Well, what we just used. We had to learn to go back and forth between mixed numbers and improper fractions, right? So what do we have to learn with compounds? Let's just say 5 foot, 2 inches. What do we have to do? We have to be able to go to the larger unit. Right? And we also have to be able to go to the smaller unit. 5 times 12 is 60. This is 62 inches. We have to learn to manipulate, don't we? 5 1/6 feet is the same as 5 foot 2 is the same as 62 inches. It's exactly the same depending on what we're doing with our measurement. We have to be able to convert it all to feet, convert it all to inches. Students like to go to the smaller unit because they don't like the fractions, but we still have to be able to manipulate our compounds before we can do some of the computations with them, just like we had to learn to manipulate our fractions. So U.S. customary units, you've got to start thinking in terms of fractions, no decimals allowed. Also, the same thing comes to play in algebra. Algebra is done in fraction format. No decimals allowed unless we're doing an application problem. And we're stuck with a messy decimal. All right, so with our compounds, can you manipulate your compounds just like you had to learn to manipulate fractions, whole numbers, and improper fractions? Can you convert between compounds to the larger unit and so forth? So let's say I have 6 gallons, 2 quarts. How many gallons is that? How many gallons? How many quarts? We've got to be able to go between the 3 different forms of our English of our U.S. customary compound. How many gallons is that? Mixed number, right? 6.5 gallons. How many quarts? 26. Because there are 4 quarts in each gallon, so 6 gallons is 24 plus my remaining 2 quarts, 26 quarts. And this is something that you have to spend time with and have to review even in 7th grade. Remember, one of the biggest faults of inexperience when it comes to teaching is assuming they know how to do that. So what do? We review it, we address it, and make sure it's not going to crop up later. If it crops up later, it's kind of too late. Then we're playing catch up. We don't want to be playing catch up. We want to know what's coming and make sure we address it properly. We don't want to create our own problem areas by assuming they know something that's needed. So then with our compounds, just like with fractions we had to learn how to convert between mixed numbers and improper fractions. With compounds, we have to learn how to convert back and forth between the compound form, the smaller unit form. Remember, all of these things are two-way streets. So, if I know someone who is 78 inches tall, convert that to a compound. What do? We're going to have to divide it back out. 72 inches would be how many feet? 6 feet, right? How many inches are left over? 6. So someone who is 6'6" is also 78 inches tall. Right? How tall are they in just feet? 6.5. So we need to be able to manipulate between all of these, whichever way is needed. So that's something that we practice and address. We don't assume. We can write our U.S. customary unit in whichever form necessary. Smaller unit, larger unit, compound. Right? Then, once we can comfortably manipulate between the three, we have to do basic operations. Basic operations on compound measurements. A lot of times it will be in feet and so forth. So let's do, we can do this. Subtraction. 5 yards, 1 foot, minus 3 yards, 2 feet. I'm still in the habit of periods. I'm trying to get rid of my habit of putting a period on my measurements. What do? Borrow. Borrow in terms of yards. I have to borrow a whole yard. What is a whole yard in terms of feet? This is exactly the same as fraction borrowing. So I'm going to borrow 3 feet, and now in the minuend I have 4 yards and 4 feet. Now I'm good to go with my subtraction. Very much parallel to subtraction of fractions. So then, 2 feet, 1 yard. 1 yard, 2 feet. So we have to do our compounds. We have to be able to add, subtract, multiply, and divide them. When I'm dealing with addition, another thing that you'll do is time measurements. Time measurements are also familiar, so when we're learning something new, let's use familiar measurements. Let's say I have 2 hours plus 3 hours, 10 minutes, plus 1 hour, 50 minutes, plus 1 hour, 25 minutes. What's the law of addition? What's the law of addition? Like quantities. So I have to obey the law of addition. I'm going to add these, and I'm going to get 85 minutes in the minute column. And I've got, seven hours in the hour column. Is that a proper way to express the answer? No. Compounds. We have to reconcile our answer. That's just like what in fraction math? What's it like?
Changing our improper fraction to...
Right, a lot of times when you have a sum with fraction addition, what happens sometimes when you have a sum? Let's say I have 3 and 2/4. I'm go ahead and give the common denominator, plus 2 and 1/4, plus 1 and 3/4. What happens all the time with fraction addition? I've got 6/4. So I have 6 and 6/4. This has to be reduced, yes, but it also has to be reconciled. I'm not going to do 6 and 3/2 for a final answer. So just like with mixed numbers, we have to take care of the improper fraction. This is just like having an improper fraction, isn't it? Isn't it? So that means I have to convert this. Too many minutes has to go, the 60 minutes have to go convert to the hour column, leaving me with 25 left over. What kind of math do we use with U.S. customary units? We use fraction math. How do we teach U.S. customary units when we're doing compounds? We relate them to fraction math. I'm not going to leave this, and I'm not going to leave that. It's no different. It's very parallel. Okay? So, compounds. All right, that's addition and subtraction. What about multiplication? What about multiplication? Let's say I have 6 feet, 7 inches times 4. Most of the time with compounds, we're not going to multiply unit times unit. That's geometry. We are going to multiply units times whole numbers. There's no restriction on multiplication. This is just like multiplying whole numbers. We multiply 4 times 7 and then 4 times 6. So I have 28 inches in the inches column. 6 times 4 is 24. I have to multiply through both the 6 feet and the 7 inches. And here again, I have an improper unit. I'd even call it that. That's an improper unit. Just like we have improper fractions, we have improper compound units. Too many inches. In fact, how many feet can I pull out of 28? 2. So I put 2 in the feet column, and that's 24. So 24, 28 minus 24 leaves 4 extra inches. All right, so compound measurements. All right, if you look in your book in chapter 8, you can see that there's conversions in objective A, there's compound math in objective B, and there are story problems in objective C. You're not going to go back and do chapter 8. We did that last semester. You're just going to do the chapter review and the chapter test to make sure your U.S. customary measurements are up to par. What about division? Let's divide a compound by a whole. Let's do 14 feet, and then we'll do 1 inch. First, we'll divide 3 into 14, which goes 4 times. That gives me a remainder, not of 2, but of 2 what? Feet. 4 feet times 3 is 12 feet. It's a good idea to keep the feet everywhere in the problem. 4 feet times 3 is 12 feet. That gives me a remainder of 2 feet, which I will put into my inch column, and that will give me 13 inches. So I'm not bringing down 2 feet. It's 24, 25. 2 feet left over, that's 24 inches, and I have an inch. So I'm going to be dividing 3 into 25, which goes 8 times with 1 left over. 4 feet, 8 1/3 inch. So everything has to be converted. This is why the U.S. customary system is so clumsy. See how clumsy it is? Why does science use the metric system? Because the U.S. customary system is clumsy. We have to keep converting. We have to memorize all of those facts, which if you weren't an American, you'd have trouble. Keeping straight all these odd names, you'd have to learn the vocabulary, and then you'd have to learn all these odd numbers. Think about it. 5,280 feet in a mile. What's a mile? How in the world did we get this mile name? You could research it historically. Some of them are obvious. A foot is 12 inches. That's kind of big for a foot now. It's really big for back, years and years ago. Inch. What is that word? Where did that word come from? You could research it. Do a paper on where these odd names come from. Bushel. Peck, quart. Well, quart is part of 4. Gallon. Think about if you didn't speak English as your first language. Gallon, what is that? I remember we've taught some foreign exchange students here, right? Several foreign students come to Bible college here, and if they're an LED major, they have to learn the U.S. customary units, at least enough to get through the class, and so they have to learn the names. It's a mess. The U.S. customary system is clumsy, but we have to deal with it. All right, so when we're dealing with it, we have to do compounds. We have to be able to manipulate between the three forms, the compound unit, the large unit, and the small unit, and then be able to add, subtract, multiply, and divide them. Okay, so fraction math is done. And once we get to the multiplication and division, you can see how clumsy it is to have to interconvert and so forth. Story problems with measurements. What's the rule about measurements and story problems? What do you have to make sure? You have to make sure that all of your givens are in the same unit. In a story problem, if you're doing an application and you're doing a measurement application maybe involving the size of a room or how much is left when you cut a certain amount. You say you have an 8-foot long 2x4, you cut off 3.5 feet. How many feet are left? 2x4, what does that mean? 2 inches thick, 4 inches wide, right? So if we're dealing with our 2x4, we sometimes have to convert between inches and feet and so forth. So make sure when you're doing a story problem that you are consistent in the units. If it's feet and inches, you have to go with one or the other. A lot of times it's easier to go to the smaller, then you can use whole number computation, or there'll be lots of fractions involved. So when you're doing your review exercises, it's on page 365 and following, there's a bunch of things involved. Story problems, there's conversions, there's compounds, and so forth. Chapter 8 test, same thing. Make sure you realize, no, we're doing all of them, not evens. But also in the book here, what we didn't do was 8.5, energy and power. 8.5 deals with the U.S. customary units of energy, which is the foot-pound. Remember, what is energy? What is work in particular? Work is the practical use of energy. Energy is the ability to do work, remember? That's kind of a vague definition. What does that even mean? So we always use work. Work is force acting over a distance. So in the English system, or the U.S. customary system, we have to learn to deal with units in physics class, and we need to learn to deal with units and formulas. Here's physical science. Here's geometry. Let's park here for just a minute and let's deal with units. Units and formulas. What have I said over and over and over about units? Units are not labels that we slap on the end. Units are part of the computation. So we've got to be able to work with our U.S. customary units in formulas. A work formula, a perimeter formula, an area formula. So geometry comes back to haunt us with units. All right? Work is force acting over a distance, okay? So we're going to multiply. Force will be in pounds. Let's say I'm carrying a 36-pound weight for 3 feet. So I'm going to multiply 36 times 3, which gives me 108. Unit is foot-pounds. That's a clumsy unit as well. Okay, then when you physical science, you're going to learn all kinds of things. There's newtons and there's joules and all kinds of things named after people. But the unit of energy and the unit of work also in the U.S. customary system is the foot-pound. Okay, what is it in metric? Gram meter, but it has a name. Okay, so what do we got here? 2 times, let's say, we've got 6 feet by 8 feet. No, 6 feet by 5 feet. Units are not an afterthought. They're not a label to slap on the end. The units are done through the problem. 2 times 6 feet is? 2 times 6 feet is? 12 what? 12 feet. 2 times 5 feet is? 10 feet. Then 12 feet plus 10 feet is 22 feet. As opposed to area. 6 feet times 5 feet is what? 30 square feet. Feet times feet is feet squared. Feet plus feet is still feet. It's one-dimensional. Remember, perimeter is the distance around. It's in one dimension. All right? Many of the 7th graders, I'm docking their grade constantly when we did the geometry chapter, because what are they forgetting? What are they forgetting to do? Put the square on the foot. Well, if they were taught to use the formula properly, feet times feet is square feet. It's not something we have to remember to do, okay? Otherwise, we have the entire assignment on the area page in 7th grade math, and every unit is incorrect because they forgot to put the square on. Well, it's not something we slap on the end, it's part of the computation. So units are part of the computation, and they put the answer in context. They're not a label to put on the end. If you are able to accomplish that with your 6th graders or 7th graders, or even starting with your 5th graders, you're going to help them in high school physical science, for sure. Okay? If you let them just be careless with their units in grade school, they're going to be careless with their units in science class. They're going to have trouble with physics. They're going to have trouble with chemistry because they're careless with their units. All right, so we will be dealing with formulas with our units. And then we also have to, on section 8.5, they might throw some odd things at you, something that I don't have memorized. And that is the idea of with energy. Energy is the ability to do work, but energy can also exist in the form of heat. And the U.S. customary units borrows from Great Britain, BTUs. British, capital B, TU, thermal unit. British thermal unit is a way to convert the work done by heat. One British thermal unit is 778 foot-pounds of energy. All right, and then, so if you're doing furnaces in the United States, they are going to be rated by BTUs. So you might have to convert something that you do not know. You don't know what it means. You don't have any experience with furnace. Neither do I. I have no idea how many British thermal units a good furnace should put out. No idea. Okay, so you might have to deal with that. Or another thing you're going to have to deal with is horsepower. Horsepower is a rate of power is a rate of doing work. Rate. What is a rate? It's a comparison, isn't it? Per unit time. And most of the time, of course, we are dealing with unit rates. So power is a unit rate. And so it's going to be in foot-pounds per what? Second. So if we are doing horsepower, one horsepower is equal to 550 foot-pounds per second. Again, we're seeing how clumsy the U.S. customary system can be. This is 8.5 in your book, and it's going to show up a couple problems on your chapter test, chapter review. This is a good way to see, can you do conversions with concepts you don't understand? I don't know about you, but I don't really have any practical knowledge of what a horsepower is. Do you? I don't know about engines. I don't care about engines. Obviously, you might want you want a certain amount of horsepower in an engine. Okay. To me, that doesn't mean anything. I could care less. I don't know how many horsepower is in a good engine. I don't know how many horsepower you need if you want to have a pickup truck and you want to be able to pull trailers and pull things with it. I have no idea. Okay. But I can still do conversion. How much power is in 4 horsepower? How much work per second does a 4 horsepower engine do? Well, what am I going to do? I'm going to use cancellation of units. And the cancellation of units will guide me through the problem. If I look, and I know I just erased it, but 1 horsepower is 550 foot-pounds per second. So I want my foot-pounds per second to remain, and I want my horsepower to cross-cancel. So this is going to tell me that this will be a multiplication, not a division. So my answer is going to be 4 horsepower cross cancels. So my computation is all right, so I'm going to be multiplying by 4. $55 times 4 is 220, so add the extra 0, 2,200 foot-pounds per second. I don't know, is that a good engine or not? No clue, but I can do the conversion by utilizing the cancellation of units technique. Okay, another common computation that will use this cancellation of units is in physics. Here's a unit rate, 70 miles per hour. If I'm going to do any physics computation, let's say I'm going down 94 at 70 miles per hour. Actually, I kind of have to go faster than that or I'm going to get run over. A lot of times with physics, you'll be dealing with momentum, mass times velocity, or force, mass times acceleration. And a lot of these things cannot be done none of them can be done in miles per hour. I have to convert this to feet per second. How am I going to do it? I'm going to let the units guide me through the problem. I'm not going to make a guess. So first thing I'm going to do is get rid of miles. There's 1 mile equals 5,280 feet. What's the next thing I have to do? I want it in feet per second. I have to get rid of hours. Hours are on top. 1 hour is 60 minutes. And then 1 minute, that's got to be cross-canceled, is 60 seconds. So if I want my answer in feet per second, I set my fraction math up so the miles cancel out, the feet remain in the numerator, the hours cancel out, and where do the seconds need to be? In the denominator, and then I do the indicated math. I'm going to cancel this 0 with this 0. I'm going to cancel this 0 with that 0. That leaves me 7 over 1 times 528 over 1 times 1/6 times 1/6. Feet remain on top. Seconds remain on the bottom. I rewrote it so I could see what I'm doing. Otherwise, my cancellation becomes messy. Divisibility rules tell me that this number, 6, well, when you add that up, the divisibility rules tell me that 6 will not go in because, yes it does, wait. 6 goes into 528. How do I know that? The sum of the digits is 15 and the number's even. So 6 will go into 528, 6 goes into 52, 8 times 48, 48, that's 88. 2 goes into 6 3 times, 2 goes into 8 44 times. So my only computation I end up having to do is 44 times 7 is 28, 308 divided by 3 twice. So it's approximately 103 feet per second. Probably in physics class you're going to be allowed to use a calculator. And then you'll have to deal with the significant digits. Everybody's favorite in chemistry and physical science. All right, so today we reviewed the U.S. customary units. You need to be able to convert them using fraction math. You need to be able to do computations with them, whether they're compounds or not. You need to be able to convert between compounds, the larger unit, and the smaller unit, and then do story problems with it, even in units that are unfamiliar. Okay, we'll see you on Friday.